In these two lectures on neural networks, we have seen every component of a neural network from its structure, defining the number of hidden layers, the number of neurons, the activation function, the output unit, to the features needed for the optimization algorithm, the choice of the loss, the initialization of the weights and biases. We have also seen different regularization techniques which may help to prevent overfitting in neural networks. The classic idea of penalization, together with the two specific layers of dropout and batch normalization, and at the end, the early stopping procedure. To conclude, let us describe the whole process of training a neural network. First of all, it is often a good idea to renormalize the data. Renormalization is, of course, more complex when you deal with images or text, which is not the case in this lecture. But it can also be challenging if you have data of different types, continuous, discrete, and so on. The next step is choosing the architecture of the network, the number of hidden layers, the number of neurons, the activation functions, and the optimization features, the loss and the initialization. Remember that the choice of the output unit and the loss function strongly depends on the type of data you have. You may also add regularization techniques as dropout, batch normalization, penalization, or early stopping. Then you can train the network. One of the crucial steps is to choose the learning rate. If the error does not change too much, it may result from a low learning rate. If the error explodes, it can result from a large learning rate. Thus, you need to find a rough range for the learning rate and then apply some recipes to tune the learning rate as the number of epochs increases. In practice, you often choose a learning rate and decrease it when the validation error stops improving. To assess the neural network performance, you need to first train the network and see if the loss is reasonable. You can compare this loss to a dumb classifier. In classification, it can be the one that always predicts the majority class. It can be a good baseline to evaluate the performance of the network. You can also run some standard machine learning algorithms like linear regression or logistic regression or tree-based methods to see if the neural network improves over these methods. Remember that for tabular datasets, tree-based methods are likely to outperform even the most complex neural networks. So using neural networks for tabular datasets may not be useful at all. Moving on, you can also check that by adding some regularization, the error on the training set increases, useful to detect some implementation problems. You can also check that if you take a small portion of the data, the network can overfit if you remove all regularization techniques. If you want to know more about neural networks, I encourage you to go to this address. You can try to understand how the performance and the decision frontier of a neural network depends on the parameters we've described so far. We will see that in detail in the lab session. I hope you enjoyed these lectures on classical neural networks. You can now look at the additional contents to learn more about neural networks.